Chapter H, Conservation of Energy, and we will start with H1, Conservative Forces. I'm going to give two definitions. The first definition is along the lines of something we already encountered, that if you fire a ball up in the air with a certain velocity, it'll go up and come back down and have the same velocity that it started with going in the other direction. And we did something with the spring too. We're going to investigate these a little bit more in this class. So definition one for the conservative force is going to be a force that acts on a body in such a way or such that when the body returns to its original position, it has the same kinetic energy it started with. And then we'll do two examples. One, gravity. I remember this one as what goes up must come down. So if you fire a ball, say throw a ball here and go upward with some velocity v initial, it'll go up and then momentarily it's going to have no velocity, still has acceleration though, and it's going to start coming down. And when it gets down to the bottom here, it'll have the same velocity, magnitude, v naught, just going in the other direction. Two, the spring, which I like to think of as, and there's no friction in these cases, ideal gravity, ideal spring. What goes in must come out. So in this case, we have a mass on a spring. Say there's some equilibrium. We'll call this reference zero. So you stretch it out. If you let go, it'll go in, go overshoot like that, ideal spring, no friction, and it'll come back and it'll be back at rest here. If you were to take the spring and say instead have it at the initial position where it's in equilibrium, and you were to say hit it one way or the other, hit it, it'll then go in and then come back. It'll be going the same speed the other way. So you just like smack it like this. Then it'll have some initial velocity, v naught, and then it'll get compressed. The spring gets compressed, and then the mass will slow down, but then it will accelerate going the other way. So it's going to be, there's going to be a force everywhere except at the beginning here, where you have no force, but then when you smack it, then you're going to have acceleration. It's going to go in and going to basically slow down, stop momentarily, and then turn around and come back like this. And at that point, it'll be traveling at the same velocity. Then it'll overshoot. It'll keep going. It'll go back and forth. We'll study this spring in more detail in terms of oscillations later. So the friction would mess things up. Without the friction, you have the kinetic energy being the same. So since the velocities are reversed in sign, you know, this one's going up, this one's coming down, and over here going this way, and then at the end's going, you know, that way, the kinetic energy is the same because you square the velocity. So it doesn't matter if it's plus or minus V naught, it gets squared, and that will be the same. Now we're ready for definition 2. Definition 2 for the conservative force. It's a force, let's say such that, a force such that the work needed to move an object from point 1 to point 2 is independent of the path taken. And now we're going to check this with gravity. And then we'll check it with friction, and I'll show you that with gravity it works. So what we do here is we have a mass M that we're going to pick up. We're going to pick it up a certain distance. So we're going to want to go a distance d. We're going to pick it up. Now the weight mg is down, so I have to apply a force that's going to be equal to mg, and just apply that to just pick it up gently until we get to this point up here. And then I'm going to take another path where I go at some angle, theta, and go and get there that way. So there's two paths. And if you do that, this is the complementary angle, that's complementary angle. And then if you have this kind of a situation, you can see that this is going to be theta up here, and alternating interior angles here, and also complement. So you can show that this angle, see here, since that's 90 degrees there, this is complementary, and then this is the same angle based on the symmetry, a line right in the middle. And then this is complementary to this angle, so that you got these thetas in 3 places. So the work, what we're going to do here in the notes, what I did is I called one the blue path and one the green path. So let's say this path here is the green path. And we have here the blue path, and we're going to compare. So for the blue path, force times distance, we have the mg force that we're applying, and it's along the line of the d. So that means it's going to be mgd. In other words, the cosine, the angle. You know, formally you have f dot d. You take the force, you take the distance, and you take the cosine of the angle between them. But if you're going in the same direction, then your force is pointing up like this, and you know your d is pointing up. So like they're in the same direction, that means the angle is 0. So if we go with the green path now, we would have, for the green path, we would have, well, we're still going to be applying the force upward, It'll be, moving a little bit, to the right like that, but the force that we're applying is upward to counteract gravity. So in that case, we're going to have here the force going up, and now the distance, d, going this way with some angle theta. We want FD cosine of theta, and because of the symmetry, there's two of them. Now the cosine of theta would be equal to, let's go ahead and put in that this distance here is C, because now this D is not the same D, it's C. So we're going to change this and make this C. All right, so we have the force times C, this distance. In fact, we should just call that the C vector so as not to confuse. It's not good to switch notation in the middle of a problem. So this distance is C. Now, when you look at my notes, everything's going to be nice for you here. Say C. All right, then C times the cosine of theta is going to be this distance, which is half of D. So this is going to be, when you, let's go ahead and write that out again here. This is 2FC cosine of theta. This is D over 2. When you look at that triangle like this, you have C, you have D over 2, the halfway point, they're going up. So the 2's are going to cancel, and you're going to get F times D, which is the mg. So you're going to get the same thing as we got before. So it doesn't matter what path you take. Now if we consider the same kind of a problem where we're on a table, say we have friction on a table, and we want to move the mass from this part of the table. We're looking down, so this is like looking down at the table from the ceiling, looking down. So we're going to want to move this, drag it up to there, and now the friction force is mu mg, and that's going to be like kinetic. It doesn't matter. We'll just use mu. And we're going to apply a force that's opposite that to just get it to go up. And here, we'll go ahead and give the other path, the green path here, and label some angles. So here we have angle theta. These are, that's complementary angles there. And then here, if we do this, theta, it's the same situation as we had earlier. And we're going to go this way, and we're going to go this way, like the two different ways, and see what happens. And here, this is again C. All right, so we have to go two ways. We got, say, D to go from the bottom to the top, and then we have the C. All right, so now we're ready to do the calculation for the blue path going straight up. We're going to want the force times the distance. They're lined up. The force is this one going up, counteracting the mu mg. So that's going to be your mu mg times d. So that's the blue path. Now when we go to the green path, we have a problem. It's different now because, see, your friction force is going to oppose you. So the mu mg is going to be this way, and it's going to be opposite you. So you have to then apply a force along the direction of motion here with a mu mg the other way. So for the green path, you're going to still apply mu mg, but now you're lined up with C. So it's mu mgc plus mu mgc. So now you have mu mg times 2c, but in this case, CD is not equal to 2c. 2c is longer distance than d, so they're not the same. So you do not have the definition satisfied for a conservative force with the path taken. And also the other definition is going to be true too. If you were to try to, say, hit this with some velocity to get it to go up there, it's going to just stop. It's not going to come back. So it's not going to come back to the same position. And the energy goes into the heat when they rub together like that. You're going to heat up the table and heat up the block. So the path is not independent because the work done along the blue is not equal to the work done along the green path. While in this case up here, the work done along the blue path is indeed equal to the work done along the green path.